Welcome to Section 3, a one-sample test for the mean. It's time to go back and look at the test for the mean that was introduced in 7.1, called the z-test. In that example, you knew the population standard deviation sigma. The question is, what if you do not know sigma? And more often than not, you're not going to know the population standard deviation. So we're going to go back through the questions from 7.1, but we're going to do them in a more realistic context. And that context is when we know the sample standard deviation in place of the population standard deviation. Now, we could use the sample standard deviation S as an approximation of the population standard deviation sigma. That means that the test statistic would now be exactly what it had been before, but instead of sigma divided by the square root of n in the denominator, it's now S, the sample standard deviation, divided by the square root of n. Notice that when we used z as our test statistic, the only thing that varied from one sample to another was x bar, the sample mean. Everything else was from the null hypothesis or the sample size. However, when we change the population standard deviation sigma to the sample standard deviation S, we now have two things that vary from sample to sample. X bar, of course, the sample mean, and S, the sample standard deviation. This gives us a different test statistic, no longer Z, now called T. T follows a different, not normal distribution that's still bell-shaped and symmetric. It's actually a family of distributions depending on the sample size. The t-distribution is also called a student's t-distribution. It requires that a random sample of size n is taken, and that either the distribution of the random variable is normal to begin with, or the sample size is over 30. Then the distribution of the test statistic, t, is a student's t-distribution with n minus 1 degrees of freedom. The degrees of freedom is another way that a student t-distribution takes into consideration the fact that there's two sources of variation in a t-distribution. So a degree of freedom can be thought of in the same way as people in chairs. If you have 5 people and 5 chairs, the first 4 people all have a choice of where they are going to sit, but the last person does not. There's only one seat left for that person. The last person has no freedom of where to sit, so only 4 people out of the 5 have freedom of choice. So our degree of freedom is n minus 1. The shape of the student t-distribution looks very similar to a standard normal curve. But as the degree of freedom changes, it varies from a standard normal curve. With the TI calculator, we have a built-in t cumulative distribution function choice. It's very much like the normal cumulative distribution function with an extra argument for the degrees of freedom. The TI-84 has an inverse, but the TI-83 does not. So we use Bell, that program that you've installed on your calculator, to solve this problem. If we want to find a student t-distribution with Bell, we enter 1 to that second question for a t-distribution and then provide the degrees of freedom. A hypothesis test when the population standard deviation sigma is unknown has the following setup. First, you state the random variable and the parameter in words. X is the random variable and mu is the mean of the random variable. Then we state the null and alternative hypotheses and the level of significance. So just like before, the null hypothesis is the manufacturer's claim or the government data, mu equals mu null, where mu null is the hypothetical mean, the assumed mean, or the stated mean. There are still 3 choices for the alternative hypothesis, that the population mean is less than what's claimed, not equal to what's claimed, or more than what's claimed. And then we choose an appropriate level for alpha. Next, we state and check the assumptions of the hypothesis test. First, that we have a simple random sample, or better that it's representative, of sample size n. then that either the population of the random variable is already normally distributed, although the t-test is fairly robust when there is a large sample size. This means that if the condition is not met that the initial random variable is normally distributed, but that your sample size is over 30, then the results of the t-test are valid. Now, this third assumption is simply ensuring that you're using the correct test. If you know the population standard deviation, then use a z-test as we did in 7.1. We're going to use t-tests only when the population standard deviation sigma is unknown. Then we find the sample statistic, test statistic, and p-value. The sample statistic is x bar, that is the sample mean, and s sub x, that is the sample standard deviation. Notice that I've changed the notation so that it matches our calculator. S sub x is what our calculator shows as the sample standard deviation, and that's just taking the place of a lowercase s. And of course our degrees of freedom are n minus 1. We'll use technology to calculate the p-value for you, and that will allow you to make a conclusion about the alternative hypothesis. And the same as before, at this point, you've seen this twice already. If the p-value is less than alpha, then reject the null hypothesis in favor of the alternative. Otherwise, fail to reject the null hypothesis and say that there is sufficient evidence to support the alternative hypothesis. Step 6 is when you state your interpretation in real-world terms of the initial problem. The conclusion for the hypothesis test is that you either have enough evidence to show that H sub A is true, or you do not have enough evidence to show that H sub A is true. So as an aside, note that if the assumptions behind this test are not valid, then obviously the conclusions you make from the test are also not valid. If you do not have a random sample, then it's your fault if you use the test. So make sure that the sample you take is as random as you can make it by following the sampling techniques from Chapter 1. If the population of the random variable is not normal, then take a sample larger than 30. If you can't afford to do that, or it's not logistically possible, then you do different tests that are called non-parametric tests. There's an entire course in statistics on non-parametric tests, and we're not going to discuss those in class. So get a sample size of at least 30, or make sure that it came from a normally distributed population to begin with. The next thing that we're going to look at is how this looks in our calculator. So on a TI, we're going to do a t-test. Okay, let's look at the first of two examples using a t-test for a hypothesis test of means. So from the website of IQ of Famous People, a random number generator was used to pick a sample of 20. So here is 20 randomly selected IQ scores of famous people. Does the data provide evidence at the 5% level of significance that the IQ of a famous person is higher than the average IQ of 100? So the first thing we're going to do is state the random variable and the parameter. Here the random variable is the IQ of a famous person. The parameter is the mean IQ of all famous people. Now the null and alternative hypotheses as well as the level of significance. The null hypothesis is there's nothing to see. The population mean among famous people is exactly the mean for everyone else. The null hypothesis is that mu is 100 for everyone. The alternative hypothesis is based on the question, does the data provide evidence that the IQ of a famous person is higher than the average IQ? So our alternative hypothesis is that the mean IQ of famous people is actually greater than 100. We're also told that alpha, our level of significance, is 5%. So alpha is 0.05. We now need to check the assumptions of this test. Well, we were told that a random number generator was used to select these 20 people. So clearly a simple random sample. We then remind ourselves that the IQ is known to be normally distributed. And then this last part is simply a reminder that we're doing the right test. We'd much prefer doing a z-test from 7.1 than a t-test in 7.3. There's only one source of variation when we're doing z-tests. There's two when we're doing t-tests. So we remind ourselves at no point were we given the population standard deviation, so we have to use a t-test. Now we're going to enter this data into our calculator, and we're going to get the sample statistics. That is the sample mean and the sample standard deviation. So let's scroll back up and let's get our calculator going, and let's enter this data. So here's our calculator, and let's go into the stat menu. And the first thing that we have to do is load this data. So with edit selected in both places, let's press enter. And you can see that I've loaded this data into L1. So 158 followed by, let's see if we can see all those numbers, 225, it looks like I'm going down, and then over 118, 150, and then to the top of the next column, 180, 122, 118, 170, 150, you get the idea. So there is the 20 data points for our, and you can see that this is the 20th entry in L1 is 118, which looks like that's exactly what it should be as well. So we've entered this data into our calculator. Now we want the sample statistics. So let's go down and do that in our calculator. So I'm going to press second quit to get back to the home screen. I'm going to go into the stat menu. I'm going to go over to calculate, and I'm going to leave it at one variable statistics. I'm going to press enter, and I'm going to use L1. If there's a value in frequency, just clear it. And let's go down and calculate that. So here's our sample mean, x bar, our sample standard deviation, s sub x. So we enter that data. There's our sample statistics. Now we're going to use that data to compute our test statistic. So I'm going to do that in the calculator. So second quit. And let's go through and do this. So the first thing it says to do is to take the sample mean and subtract the assumed mean. So 145.4 is the sample mean. I'm going to subtract the assumed population mean of 100. I'll press enter because I didn't use grouping symbols there, so that invokes that subtraction. I'm then going to divide this, and to force everything to happen in the denominator, I'm going to open parentheses down there. The sample standard deviation was 29.27. That is the sample standard deviation. I want to make that into the standard deviation of the sample means. So I'm going to divide that by the square root of 20. I'm going to arrow out of that radical and close those parentheses. So that closed parenthesis is outside of that closed parenthesis outside of the radical. You can see that it's a little bit bigger and to the right of the radical symbol. So when I click enter, I get my test statistic. That's taking the place of our z-score, but there's other things going on as the curve is made more compressed than the standard normal curve. So our t-score is 6.93 and change. And now, of course, we want our p-value. We could use Bell for that, or we could simply use the t-test on our calculator. So let's do that. So I'm going to go into the stats menu. I'm going to go over to tests, not a z-test, but a t-test. So I'm going down to 2. I'm going to press enter. I'm going to use the data from L1, so I'm going to leave data selected. Mu sub 0 is 100, in other words, the assumed population mean. I'm using L1, and let's go back and see that alternative hypothesis there. The alternative hypothesis is that the mean IQ of famous people is actually more than 100. So when I go down, I want to select more than. I can draw this or calculate it. Let's start by calculating it. and it says that the p-value is, well, pretty darn close to 0. There's 6 zeros between the decimal point and that 6522. So we're going to enter that as 0 in our test, our p-value. So the probability of getting a value that extreme by chance alone is essentially non-existent. Let's go back in and see the curve, because this will draw a student t-distribution for us. So I'm going to go into stat, I'm going to go over to tests and down to a t-test, and then I'm going to leave all those settings and I'm going to go over to draw. And it will show me the student t-distribution, and then it will shade the area that is with a t-score of 6.9. It's probably not even on here, so it looks like nothing was shaded, and it's telling us our p-score is 0, which we've already concluded. So our conclusion is that our p-value is less than alpha, so we reject the null hypothesis. Now we go back to the question itself and we state our answer in terms of what we were asked to do. We were asked, does the data support the claim that famous people have higher IQs than the average? And we would have to say yes, there is sufficient evidence to support the claim that the average IQ of famous people is higher than the average IQ of all people. Okay, one more example, this time the lifespan of European males. In 2011, the average life expectancy for a woman in Europe was 79.8 years. The data in table 7.3.2 are the life expectancies for men in European countries in 2011 from the World Health Organization. Do the data indicate that men's life expectancy is less than women's? And we're testing this at the 1% level of significance. So a fair amount of data. It looks like all European countries are included in this. So let's get going. So the first thing we need to do is state the random variable and the parameter in words. The random variable x is the mean life expectancy of males in European countries. The parameter mu is the mean life expectancy of all European males. So the null hypothesis is that there is no difference. That is, the mean life expectancy of European males is the same as the life expectancy of European females, namely 79.8. Now the alternative hypothesis is that the life expectancy is less than the life expectancy for women. So when we create our alternative hypothesis, we're claiming that the life expectancy for men, mu, is less than that for women. We were told that the level of significance is 1%, so alpha is 0.01. The random requirement doesn't look like it is required here because it looks like we have every European country. There are some really small European countries that may not have been included in this, but n equals 53. So we don't have to worry about the sampling method because it looks like this was a census. So n is greater than 30, so the random variable can be assumed to be normally distributed. And that last requirement is simply that we're doing the correct test. The population standard deviation sigma is unknown, so we are correct to do a t-test and not a z-test. So now we're going to go into our calculator and we're going to get the sample statistics. And to do that, we need to load this data into our calculator. So let's turn it on. Let's go back to the home screen. Let's go into the stat menu and let's edit that. So I've entered this data into L2. So you can see in L2, I've entered all 53 of these data points. And you'll be doing a lot of this, so get good at checking your entries with the calculator. If you're wrong, it probably won't be because a 65 was entered as a 66. It'll probably be because a 65 was entered as a 6 and a 5. So you can check in broad terms relatively quickly. So there's my data in L1. I want the test statistic. So I'm going to go back to the home screen. and I'm going to go into statistics. I'm going to calculate one variable statistics for that data. Of course, now my list is in L2. This is useful to do, especially during an exam. If you have two questions that require lists, you can keep those lists separately, so don't overwrite it. So if you want to check and go back and look at another question, you've got a whole separate list for it. And it's easy to change lists. Notice that above the 2 key is L2 in blue. So I press second and 2 to get L2. And then I go down to calculate. And it tells me X bar is 73.73. So there is my sample statistic. And notice that that is significantly less than the life expectancy for women in Europe, which is 79.8. So our average already looks like there's something to this, but of course that has to do with the standard deviation and the distribution of the data. S sub x is 5.7283 and change. So we've entered both of those. Now we're going to compute the test statistic, and that is exactly what you'd expect. The only difference is that we're using S sub x, that is the sample standard deviation, instead of sigma, the population standard deviation. So when we go through and do that in our calculators, we're going to, well, let's go back to the home screen. Let's enter that sample mean, 73.7358. And from that, we're going to subtract the mu sub 0, the assumed mean for this population. If there was no difference, it would be 79.8 if men and women had the same life expectancies in Europe. I'm going to click enter because I didn't use grouping symbols. So it looks like those averages differ by 6 years. I'm now going to divide to go into the denominator. I'm going to open parentheses to force everything that comes after it to stay in the denominator. Then I'm going to enter the sample standard deviation, 5.7283. I'm then going to divide that. Usually if you put divide and then divide again, you're staying in the denominator is basically what that says. But of course, divide and then a divide again when you're in the denominator means that that square root of 53 is actually in the numerator, but we don't have to worry about any of that if we use our parentheses correctly to say, just stay down there. I'm then going to grab a radical and put 53 inside it. I'm going to arrow to the right to get out of the radical because I need to close those parentheses to tell the calculator that all of that stayed in the denominator. I'm then going to press enter to have it compute this, and it tells me that the test statistic t is negative 7.707 and change. Now, of course, we want the p-value so we can compare it with alpha so we can make our conclusion and use that for our interpretation. And to do that, we're going to go into the stat menu and we're going to go over to tests and down to a t-test. Press enter. We're using the data. The assumed mean is 79.8, so I'm going to enter that, 79.8. I'm using L2, so I'm going to press second and then 2 to use the data from L2. Our alternative hypothesis is that the true population mean for European men is less than mu sub 0. And so I'm going to go over and enter to select that and then down to calculate. So let's make sure that we got the same numbers here. So we had calculated this and we got that X bar is 73.7358. That looks correct. We got that S sub X, the sample standard deviation, was 5.7283. That looks correct. N equals 53. That looks correct. And of course, our test statistic, negative 7.70693 and change. That looks like what we got earlier as well. So now we can record our t-score, or our p-value, mind. Our p-value is essentially 0. And we can see that because that exponent is negative 10. There's 9 zeros between the decimal point and the 18534. That's as close to 0 as you're going to get. So when we state our conclusion, we compare this to alpha. 0 is less than any level of significance, so we reject the null hypothesis. That means that there is sufficient evidence to support the claim that the mean life expectancy of European men is less than that for European women. And that concludes our first look at hypothesis testing. Next time we'll look at confidence intervals. A lot of good stuff in this section tying back to previous things and opening the door to new ideas later in the semester.